Hello, ninth graders. Oh, a lovely evening. Well, it's probably morning for all of you. This is Mrs. Johnson coming live to you from Mrs. Johnson's kitchen. Yay! Oh my goodness. Look at how many onions I have on my counter. That's a little bit weird. All right. As all of you know, we are learning from home right now, and all of you took some time on Friday. Well, I should say most of you, I shouldn't call out who I saw did not log in, but for all of you who did log in and complete pages 79 and 80, you would be familiar with this page of notes that you filled in on Friday. This is page 79. So a quick recap from Friday's notes. When you're looking at a table, you can tell if it's linear if you can see a constant rate of change, and you can see an adding pattern, and that would also make it an arithmetic sequence. So whenever the table looks arithmetic, it's gonna be linear. So linear, arithmetic, same kind of thing. Now, if you have a straight line and a constant rise over run, it's also linear. So if you're just looking at a graph, you can tell it's linear. And then for an equation, the two things that make it linear, it's kind of hard to see over there, but it would be in slope-intercept form, so in the form y equals mx plus b, and more importantly, for a linear equation, there's going to be no exponents on the x or the y axis. Some of you might have wondered why I did not connect the dots here. We talked about this a little bit in class. This is not a continuous function. So you are not spending money at the fair every time in between the rides. You spend money when you go on the ride, but it doesn't rise in between. So that's why you'll see those separate dots there. Is it nitpicky? Sure, but that's me. Okay, let's look down here. On this one, we know that it's exponential because it had a constant change factor. The word exponential goes with geometric sequences. But here, the change factor is 3. It was multiplying by 3 every time. When we are looking at the graph, it is a curved graph. Technically, we could have left this one not connected, just if this person was not depositing single amounts every month. And also, each point is 3 times the last point. If you look at each dot here, they grow 3 times each point. And lastly, to tell if an equation is exponential, dun dun dun, it has exponents with the x value, and it's also not in slope-intercept form here. So that was what we talked about on page 79. The reason I wanted to recap that quick is because on page 81, we are now talking about rates of change. Now, we reviewed page 79. Now I want you to look at the 2 things we're going to be having to do on page 81. For each representation below, do the following. Determine if each representation is linear or exponential. Then, if it's linear, you're going to find the constant rate of change, and if it's exponential, you're going to determine the change factor. So constant rate of change is what it's adding every single time. Constant rate of change only goes with linear functions. Change factor is what is being multiplied each time. And as we learned on Friday, change factors move a lot faster than a rate of change because multiplying changes much quicker than adding. So the exponential equations will all have a change factor. So in just a moment, I would like you to do all of these problems, just part A. So on each of these problems, you're going to write down part A, part A, part A on each of these, and I want you to look through these 6 examples and try to determine if they are linear or if they are exponential. And if you need page 79 to help you out with this, go ahead and pull that out now. I'm going to give you a second right now to push the pause button because it'll probably take you longer, and I am going to jump right into the explanation right now. So if you did not choose the pause button, then that means that you did not listen to my directions. Shame on you, but there's no way for me to know. All right, let's talk about number 1. Number 1 is linear. The way that we can tell it's linear, there are no exponents on it, on the x or the y. Number two is exponential. I can tell it's exponential because there's an exponent on the number 3. It's 3 to the power of x. All right, number 3 is exponential. This one, I hope, was one of the easiest ones on this paper because whenever you see a curved graph like that, it's going to be an exponential function. Number 4, I had to look at number 4 and actually see what was happening here. So I'm going to draw my little swooping arrows, and when I look at these, I can see that it subtracts 18 repeatedly to get from every term to the next. But remember, you don't just check one side, you also check the other side, where it's adding 2. This is going to come more in handy when we get to part B, but get into the habit of always checking both sides. Now, because there's a constant addition pattern, yes, you are adding, even though it says minus, that's just adding a negative number. Part A is going to make this linear. Okay, number 5. Number 5 is a straight line. Ladies and gentlemen, that is a linear function. And then lastly, on number 6, now on this left side, it's adding 1. You might be tempted to say, oh my gosh, it's adding 1, that's linear. Check the other side. The other side is not an adding pattern. The other side is technically dividing by 3, but we learned in our last unit we do not write divide by 3. We always change it to multiplying by some change factor. So dividing by 3 is the same thing as multiplying by 1/3. So I'm going to keep multiplying by 1/3 here. Now remember, if you're having trouble seeing what the change factor is, especially when it's a fraction, we talked about it in class where you can take a later number and divide by the number in front of it. Because if we're trying to figure out what got multiplied moving down, we can divide it backwards and that will give us our change factor, which in our last unit we called R. All right, so for this one, exponential because it has a multiplication pattern. All right, so we did part A for every single problem. Over here in the question/notes, I'm gonna write a little note to myself. So I'm gonna start by talking about constant rate. Sorry, I don't know why it goes out of focus. Well, I do, it's because the camera does that. Constant rate of change. So here's what I want to say about the constant rate of change. Constant rate of change is always going to go with linear functions and linear equations. Now, the ways that we've talked about this constant rate of change in the past, we've called it m before, that's a slope, and we've also used the letter d for that common difference in our last unit. So those things might be more familiar when we're talking about the constant rate of change. Then I'm going to write a little note on change factor. Now a change factor is only going to go with exponential functions. And the letter that we got used to in the last unit for a change factor was the letter R. So what we're going to do now, for every linear equation, that would be numbers 1, 4, and 5, we're going to find the constant rate of change. And for all of the exponential equations, number 2, 3, and 6, we're going to figure out what the change factor is. So going back to problem number 1, I want to figure out what the constant rate of change is. The only issue that I have here is that this thing is not put in slope-intercept form, and it's harder to see what the slope is when it's not in slope-intercept form. So I'm going to begin number 1 by solving for y. I'll divide by 3 on every single term, and when I do that, I get y equals 2/3 x minus 3. So once I have it solved for y, it's easy to figure out what the slope was. M is right there as 2/3. So what I'm going to do for part B is I know that the constant rate of change is 2/3. Yes, that is M, that is D, but I'm just going to write constant rate of change as 2/3. All right, let's look at number 2. So number 2, part B, because this is exponential, it's not going to be a constant rate of change because that's an adding pattern. This one's going to be a change factor, a multiplying pattern. So I go back to what we learned in our last unit. 2 is not what it's changing by. 2 would have been the initial value. 3 is going to be how it changes because that would be where R falls in that equation that we had from our last unit. So I would say change factor is 3. All right, let's go to number 3. Sometimes people have a little bit more trouble because we haven't had a ton of experience here finding a change factor from an exponential graph. So I'll show you how we do that. I'm going to begin finding the change factor. I'll write that in here. And what I'm going to do to find the change factor in this exponential graph, I'm going to begin by putting dots in the corners that the graph passes through perfectly. So this corner passes through 1. Then it passes through 2 perfectly. It doesn't pass through 3, but it does pass through 4. And then the next one that it passes perfectly is 8. I hope you're starting to see a pattern. How do I go from 1 to 2 to 4 to 8? What's being multiplied on the right side? And what you'll notice is that pattern is multiplying by 2 on the right side. So that means that the thing that was being multiplied here was 2. That's my change factor. All right, we already did most of the legwork on this problem when I drew in all these swoops. So for part B on number 4, our constant rate of change is going to be the change in y values, which here it was changing by -18 for every y, divided by the change in x values. And on this side, it was adding 2. So it's not always going to change by the same number every time. So you're looking at the ratio of one side over the other. So this one, -18 over +2. So if I were to do that, -18 over +2, my constant rate of change is actually -9. The most common mistake that I'll see on a problem like this is that people try to just tell me that it's -18 because they get so excited that they see the pattern that they forget to check the other side and divide by that. Sometimes you'll see -18 plus 2 over here, and then it will change by a -9 and a +1 over there. And that's where people also get nervous because they think, oh my gosh, I did something wrong. No, because when you do -9 divided by 1, you still get the same constant rate of change. It just showed up with a smaller gap in the table in situations like that. Okay, let's look at number 5. On number 5, we have got a linear graph. So I'm going to be looking for part B, a constant rate of change. And like we said over here, it's always either the slope or the common difference. Here in a graph, we're looking for that slope. So I am going to look at these very nice corners that are drawn in here. Sorry, my arm's getting stuck in my weird little tripod here. This graph is going down 2 spaces to the right 1, down 2 spaces to the right 1, down 2 spaces to the right 1, down 2 spaces to the right 1. Obviously, there's a pattern here by going down 2 to the right 1. There's my slope, which means my constant rate of change is -2 over 1, which reduces to -2. That's my constant rate of change. So again, we just did the rise over run. All right, lastly, number 6, our exponential. This one is going to have a change factor. And the change factor here is what's being multiplied as you go from one term to the next. So on this one, because it's moving every single space, we can make our change factor 1/3. If this was moving 2 times every space, then we'd have to be a little bit more clever about what it changed by every single x value. And we'll see more examples of that as we move on. All right, so we did all of part A and all of part B. I want you to look at this table down here. How to recognize different functions and their change. So when we're looking at an equation, a table, and a graph for linear and for exponentials, I want you thinking, what the heck did we do for a linear equation? What the heck did we do for a linear table and for a linear graph? I'm gonna give you, I don't know, it shouldn't take you more than like 2 minutes. Push pause on the screen again and try to fill in this thing. What could you do to remember how to find the rate of change in each of these scenarios? And after your little 2-minute break there, I'll give you some of my ideas. All right, hopefully you have something written down because now I'm going to talk about what I would suggest you add to this. I always think that it's important that you write down your ideas because you usually remember yourself better because you're all such vain people, and I love it. It means you've got tons of self-confidence. All right, so let's talk about equations. First thing we did for our linear equation was we solve for y, put it in slope-intercept form. So I'm gonna say down here, solve for y. Because once you solve for y, you're going to get m. And when we're finding our rate of change, you're gonna use slope. Whatever that m is going to be your constant rate of change. All right, now in a table, what I did in my table to find the constant rate of change, I drew swoops. I'll remind you what those were. Up here, I did these little swoopy things to tell you what was changing every time. So after I drew in these swoops and found that pattern, I did change in y as my numerator divided by change in x. And that's another way that we've talked about in the 8th grade and just in the past in the 9th grade to find slope. So again, we're just using that slope from the table. Lastly, in a graph, it's going to be the rise value over the run value. Guys, once again, that's slope, okay? So rate of change here, don't forget, it is slope in all of these situations. We just have a fancy word for it. It's not even that fancy because you've heard that word before. All right, so that's constant rate of change. Now let's talk about exponentials, which are new and scary, but also fun and like awesome because look at, who doesn't love that curve? Oh my goodness, so beautiful. All right, so in an equation, to find our change factor, we took the number that is directly below the exponent. So I'm going to write down here for equation the number directly below the exponent. All right, so that's how we find change factor in an equation. Now, if we go back to the table here, our change factor, we just looked for a multiplying pattern. This was changing by 1, so whatever the multiplying pattern was ended up being our change factor. So I'm just gonna say, look for multiplying, I hope I spelled that right. Actually, I don't care, pattern. Okay, so we've got equation, we've got a way to find the change factor in a table. Let's talk about that graph. The graph, we drew in some nice dots, and then we looked for the distance between those points. We looked at how you went from one dot to the next. So I'm gonna say, draw dots, look for multiplying pattern. And whatever it's multiplying to the right, that is going to be our change factor. All right, so this was our page of notes for today, page 81. If you didn't have it, hopefully you found it on the Canvas because we linked the digital copy of these. But then what I want you to do now is, oh gosh, I can't remember what the homework assignment is. I think it's linear versus exponential for tonight's homework, but I will make sure that I put it correctly in the Canvas page. All right, I miss you already. Goodbye.